Yeah. So thanks, Florent. Thanks, Nati, for disrupting the schedule. Yeah, so I remind you where we left at. We wanted to study kernel ridge regression, so I wrote here the formula. And in the last lecture, I gave you a 15 or 20 minutes introduction to what is, RKHSs and kernel ridge regression. And in fact, this optimization problem has an explicit solution in terms of the kernel matrix, the empirical kernel matrix, and the kernel function. Okay, and as you will see, the results that I state rely heavily on this explicit form, and in fact, I can state right away. I think what's an interesting open problem. Open. Redo what I will do. Explain for other losses. I think this is a very interesting open problem. Okay, so the first question we should ask ourselves is which kernel we should choose to make contact with neural networks, and okay, recall that we are interested. I mean, the case that we wanted to study is that of linearized two-layer neural networks. So this is equivalent to say that linearized two-layer network are linear models with the feature map being, this is the number of neurons, this is the input dimension, and then sigma prime W1 transpose X, X transpose blah blah blah, sigma prime Wn transpose X, X transpose. Okay? Okay, and of course, you can always write ridge regression with respect to such a featurization map. So ridge regression in this setting. So ridge regression with feature map phi is equivalent to kernel ridge regression with respect to a kernel that is k, let me call n, subscript n, to say that this is the finite width kernel x1, x2, that is just the inner product phi x1, phi x2. Okay, so perhaps I should stop because I should check whether this is clear to everybody. This is a very basic fact for anybody that studied RKHS methods, but perhaps for somebody that is new, it's not hard to see, but
what are capital N and D again?
Oh, so good question. So here I remember that we were looking at two-layer neural network with input dimension D, and then n hidden neuron and one output unit. Okay, and when you linearize around the initialization, the linearization is just a linear model with a feature map phi that we computed, right? I don't know. I don't remember what. Is that okay? That answer your question? Okay. So any question? Is that okay with everybody? Okay, fantastic. So now what is this kernel? This is 1 over nd, if I compute the thing, x1, x2, and then sum over I1 to n, sigma prime wi transpose x1, sigma prime wi transpose x2. And if I compute, if I think of going to infinite width, at least point-wise, it's obvious that by the law of large numbers, this converges to 1 over d Okay, let's write it. K x1, x2, that is 1 over d times x1, x2 times the expectation with respect to w. The wi's we are taking I at d of sigma prime w1 w transpose x1 sigma prime w transpose x2. Now I'll take the initialization to be the standard initialization in these cases, that is the wi are uniform in the sphere in d dimension. I could take them Gaussian with covariance I over d, but this is a little bit more convenient mathematically. Okay, and if you assume this, then clearly this is invariant under rotation. If you rotate both x1 and x2, this doesn't change. Now, it's a convenient simplification to assume that my data are always normalized. So I'll assume that data are normalized to be of size square root of d. So each entry of x is typically of size 1, and so the L2 norm is square root of d. If you fix therefore the norm, and this is invariant, this must be a function must be some function, possibly depending of the inner product x1, x2. And let me in fact write it without loss of generality. I can put it here a factor 1 over d, right? This is just a redefinition of hd. Okay? So the limit kernel of this two-layer neural network in the linear regime is an inner product kernel. How does this depend on the dimension? Well, does this make sense? Is this okay with everybody? How does this depend on the dimension? Well, I claim that HD is roughly independent of D in the sense that HD of, let's say, Q, this converges as D goes to infinity to some H of Q. So this is a claim that I'll try to justify. Okay? So basically, all the dependence of D appears in here. Okay? I'm interested in this claim because I'm interested in large dimensions, of course. And I'm interested in large dimension because what, as we said, this interpolation not hurting is a typical high-dimensional phenomenon.
So here the expectation in the second line, does it depend on the dimension?
This expectation is with respect to W being uniform in the sphere. So W is a d-dimensional sphere. So this, in general, will be a function depending on the dimension, right? So why I claim that this is roughly independent of the dimension? Well, because I claim that for large dimension, so I'll be sloppy, but for large dimension, I'm taking W uniform on the sphere, but for large dimension, this is very similar to taking it normal with mean zero and covariance I over D, right? You know that in high dimension, a Gaussian vector, isotropic Gaussian vector, is basically concentrated on the sphere. So this will be true. And now if this is normal, these are two Gaussian random variables, G1 and G2. If you fix x1, x2, these are two Gaussian random variables. And what is their covariance? Well, it's very easy to check that the covariance. So these are normal, 0. And the variance is identity because the vector x1 has norm square root of d, and the covariance is x1, x2 over d. So because of that, you get this thing when the W is Gaussian. This is H of x1, x2 over t. So this H of Q, in fact, is a completely, all right, it's a convenient representation. So H of Q is just Q times the expectation of sigma prime G1, sigma prime G2, where G1 and G2 are jointly normal with covariance, with correlation Q. Okay? So this is the structure of the infinite width kernel for a 2 layers neural network in the linear regime. It's just a function. You can basically forget this dependency around D, or okay, if you have to write proofs, you have to take carefully care of it, but for intuition, it's good to forget it and then. Well, when I said here that by rotation invariance, this depends only on the inner product, if they are not on the sphere, can depend also on the norm. There are other two invariants, that is the norm of x1 and the norm of x2, right? But other question, yeah?
So what is happening to n, the number of units? Is that just...
It's going to infinity, right? This is n going to infinity. So here, all of this is heuristic to tell me what is the kernel that I'm interested in. Now, in the next lecture, so the question is, an interesting question is then, how fast this convergence happens, and this is what I'll address in the next lecture, right? Can we continue? Of course, point-wise, the law of large numbers tells me, point-wise meaning for a fixed vector x1, x2, the law of large number tells me, but I don't care of a fixed vector x1. I care when I plug these into the regression, what happens, right? So an error that can be very small in this approximation can in principle become very large when the sample size is large, right? Okay, so this is the kernel that I'm interested in.
Yeah. It isn't obvious to me why at infinite n, the kernel at finite d is different from the kernel at infinite d. This function hd versus function h. Can you explain again why these are not the same function?
These functions, well, because the W is not normal, right? There is a difference in this expectation. What changes is this expectation. Here I'm taking the expectation to be with respect to W uniform. I could have started with the W Gaussian, but then that poses some other technical complication. So the result that I'll state, we proved it for W on the sphere. And so this is what I stick with. And the pain that I have to deal with is this small dependence over D.
So if W had been Gaussian, then these would be the same?
Then this would be just independent of D. Thank you. Okay, it's great that there are questions because this is really fundamental, right? So, okay, so excellent. Now let me make first state one fact, and is I will assume for technical reasons we'll assume basically HD of X. So this is a Taylor expansion. Okay, you can check that it is. If sigma prime is in L2, it has a Taylor expansion. CL of D over L factorial X to the L. This will be a convergent Taylor expansion. So here there is no assumption, but the assumption is that, okay, it's always true that CL of D. So this is actually a nice exercise. We'll assume. So exercise. This is true if sigma prime is nice. For instance, it's in L2. So the thing that I will assume is that CD of infinity is strictly positive. CL of infinity is positive for each other. Okay, this is not really needed for the results, but as you will see, I mean, it's a little bit convenient to state things a little bit more conveniently, more easily. This means basically that the activation function is generic. For instance, it's satisfied if you take RLU with a shift, with an offset. Okay, so now before going into stating things, let me make a remark. So consider a multi-layer network, so L-layer networks. Just a standard feed-forward network. So f of x is sigma composed with W1, composed with sigma, composed with W2, composed with blah, 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 composed with WL times X. Okay? So the standard architecture. So if I take the standard initialization, in which the W, all the weight matrices WI, WL, IJ are, IID normal, 0 with some variance that depend on the layer index. Then the corresponding NTK kernel, is also an inner product kernel. So you can go through the whole process of constructing the linearization of this, taking the infinite width limit, etc. This will give you a kernel x1, x2. Okay, that depends on the number of layers, on the activation function, etc. I claim that this kernel will always be a kernel that is an inner product kernel. Is this clear to everybody that this is true? This should be obvious. Actually, I claim that I don't have to do any computation to claim this. And it's obvious because this is rotation invariant, and the linearization is rotation invariant. And any function of two arguments that is rotation invariant depends on the norm of this, on the norm of this, and the inner product. The norms are fixed, so it depends on the inner product. Done. So what I will say apply to infinite width kernel for any fully connected neural network in the standard initialization. Okay, it doesn't apply.
Here you're assuming all the weights are Gaussian or just the last layer?
All the weights are Gaussian at the initialization. And in fact, are distributed with any rotation invariant distribution applies. If I take the initialization of this metric to be U sigma V transpose, where U and V are orthogonal, hard distributed, then this will also apply. Yeah.
I thought in the NTK there is a 1 over square root of D factor and the weights are initialized from a standard Gaussian. Over here there is both a 1 over square root D factor and the weights, and the weights are still initialized from the Gaussian with variance 1 over D. So there seems to be an additional 1 over D factor. Or
well, I mean, here the weights are initialized with 1 over root D factor. This is this 1 over D that you show here. That's it. I mean, this is the only initialization that makes sense, right? The only scaling that makes sense, because otherwise this inner product is not of order 1. Right?
there is outside growth of a factor of 1 over D.
This factor 1 over D doesn't matter, because since we are doing linear, if you multiply the kernel by a constant, this doesn't change the regression. If you do linear regression, you multiply your design matrix by a constant, the linear regression doesn't change. This just as a factor, comes in as a factor in your coefficients. So
Maybe it would help to say where the 1 over d came from there. Like,
where did I put this 1 over? I just you'll see this is just you see it's just convenient because now I have 1 over d and I can write this x1 x2 over d, right? I argued that this function depends only on x1 x2 over d, and then you have a factor here x1 x2 over d. So this is why I put the 1 over d to simplify my formulas. But I could put here e to the d. This wouldn't change my regression at all. Okay? Okay, thank you for the question. Okay, so excellent. So this was remark 1. Remark 2 is that the kernel changes for other architectures. For other architectures. So for instance, if you take convolutional, two-layer convolutional networks or convolutional networks with avalanche pooling, then the kernel must become, so here I'm thinking the kernel must become translation invariant. So I'm thinking now of X as, for simplicity, let's think of X as a one-dimensional signal. So convolutional network normally are applied to images, but just to write formula, let him think that our image is a one-dimensional signal. So our image is just a vector. So this is my image. And convolutional network have the property that are invariant over their translations, the group of translations of this image. One-dimensional images, what means to do a translation? It means to do this, right? This is L plus 1, and then L minus 1. So this is a cyclic group of translation. Okay, and you can go over the computation or simply believe me. In this case, the kernel will take the form of 1 over d sum over L 1 to d, or 0 to d minus 1, of h of x1 TL x2 over d. So the kernel must be invariant under rotation, under this translation group. So it makes sense that it must be somehow, the simplest way to make it invariant starting from this is just take this kernel and average it over this translation group. And in fact, if you take a two-layer neural network or a multi-layer neural network with average pooling, you can check that this is no, a two-layer neural network with average pooling, you can check that this is the case. Okay?
Question. So here in TL, what are the indices?
Oh, sorry. This is TL of X. I was missing one symbol. So this is how the group of translation acts on X. So TL of X is a vector. Right? And what is TL of X is just what you obtain by taking X. Cyclically, okay? So perhaps I should draw a picture. X1, X2, blah, 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 blah. XD, this is my image, and you rotate it by L. And I can repeat this, of course, with the group of translation on the torus, etc.
Another question regarding the previous remark. So when you write H, is it H or it must be F in the end?
This is H. This is the kernel. This is not the target function.
So then what was the claim of your remark?
The claim is that if you take an L-layer neural network, this is what an L-layer neural network is, a parametric family with parameters W. Now, I can go for this neural network, go through the calculation that we did last time, and compute the linearization of this multi-layer neural network. The linearization around initialization is something conceptually trivial. It takes a little bit of 3 lines of calculus, really. But it takes a little bit of calculus. You write the linearization, and then you compute the associated finite width kernel.
Okay.
And then you compute the limit of very large width. You get a kernel. I claim that you don't need to do this calculation. The kernel will be a rotation invariant kernel just by symmetry. So it will be this form. So the results that I will state will apply to any kernel that you obtain that way. So to any infinite width network in the linear regime. Now, the results that I state will not apply to this case, to the convolutional kernel, but there are extensions for that case. By the way, at this point, perhaps I should mention that most of this work is joined with Theo, that is sitting there and is the world expert on all of this stuff.
Sorry, I missed if you said what happens if you limit in the convolutional.
So if you take the infinite width limit in these things, you get a kernel, and this kernel takes this form.
The infinite D.
Infinite D limit. Well, infinite D, this is what we didn't do even in that case. Oh, you mean how does this depend on D?
Yes.
Well, it's the same, right? This, once you put this factor 1 over D here, this dependence you can forget. Okay?
Just remind me, the axes are normalized to D or to 1?
The axes are normalized to square root of D, right? All the entries. Does this answer your question?
Because there you took it, but just to write the function h, right?
Sorry?
Because there you took the infinite limit to write
Yeah.
but
Yeah, but so what I'm saying is that, in large D, this thing will not depend on.
but you still have to put all the translations.
Yeah. All of these factors, right? So this function, you can think of it as independent. Okay, so here there is another, I think, interesting open problem. Is that, so now the program is what? We want to analyze program. One. So one want to analyze in theory is when the risk of kernel ridge regression for, what is the risk of kernel ridge regression for a given structure of the kernel K? When is n large enough so that the finite width kernel, or the risk of the finite width kernel is close to the risk of the infinite kernel. And 3, when do neural network, when are neural networks better than kernels? Because if they are never better than kernels, then you might as well use kernels that are nice, convex optimization problem. Okay, so I can say that these two have been done to some extent or to some degree of accuracy for inner product kernel and for these convolutional kernels. And 3, for 3 we have only special cases, special examples that I'll briefly mention. And so this poses a couple of open problems. So open number 1 is repeat 1 and 2 for other architectures. I think this is very interesting because this, even if the linear theory is not that good, that accurate, it captures something. And so repeating this for other architecture can really provide some guidelines as how to match architecture to data that I think it's practically is the most important problem, or one of the most important problem in this area. And open number 2, wow, understand, solve 3. This is a very big problem, I think. I mean, there is n papers over this that show special cases of gaps of this, but I don't think there is a general useful theory in any way. Okay, now that we did a lot of introduction, I can state a theorem. Okay, so what is the setting for this theorem? Setting for theorem. Okay, I will have an inner product kernel. Under this assumption there. And I assume data, so x1, xn will be IAD uniform on the sphere of radius square root of d in d dimension. And the yi will be some function of xi plus noise, where the noise will be independent of the xi and mean 0 and variance, let's see, 2 square. Okay, so I will make no assumption about, so the distribution on the axis is very simple, they are uniform, but I will really make no assumption on f star. Well, I have to make one assumption for things to make sense, and the assumption is that f star must have finite second moment. Or equivalent finally L2 norm. This is something that I have to make, right? Because since I'm computing the test error is this one. If this doesn't have finite second moment, then I really cannot hope that the test error is finite second. It's finite, right? But other than f star is general. This is a theorem. So this is proved with Song Mei and Theodore Misakevitz. And it says the following. Okay, under these assumptions, there exists lambda 0 positive such that for any lambda in, let's say, 0 plus lambda 0, by 0 plus means that, okay, let's write 0 lambda 0. And the interpretation of lambda equals 0 is, of course, that you are looking at the minimum norm interpolator. The following happens. if n is smaller than, let's say, d to the L plus 1 minus delta, and bigger than d to the L plus delta, for some positive constant delta. So think of delta as 0.000001. Then the risk takes a very simple form. So what is the risk, of course? So let me write it here. Okay, let me write it here. The risk is, I'll write this notation. This will be the excess risk, right? So the expectation of f at lambda x nu minus f star of x nu square. So this is the test error for the function f star when I use regularization parameter lambda. I claim that this will be the projection. Okay, I'll write it and then I'll say what it is. Okay. Okay, so what this is I take the target function f star, this is the true function that I'm trying to construct it, and I project it onto polynomials of degree bigger than L. Okay? So this is the projection of f star orthogonal to polynomials of degree less or equal than L. Okay? Equivalently, this is equal to the mean over all P that are polynomial of degree L. Let me write calligraphic PL of the expectation of f star of x minus p of x. So this is the optimal error that you can achieve by approximating f star with a polynomial degree L. And then there is a small, so this is the risk, and then there is something that goes to 0 when n and d go to infinity. Further, no RKHS method with inner product kernel can do better. So if I stick to an inner product kernel, if I change lambda basically or change loss function, I'm bound to behave this way. Okay, this is the statement of the theorem. I'll next comment on the intuition for this, but perhaps I should pause and ask you if the claim makes sense.
So just a question, when at the beginning you were stating the open problem for the other losses, but now you're saying that the other losses cannot do better.
Cannot do better when in terms of this test error, right? But here I'm looking at.
Oh, okay, you would also need to change this.
Right. You can look at classification error.
Okay.
Other question, yeah.
So for the interpretation of this, like for arbitrary layers, we always get dot product, and they always perform the same?
They always perform the same, yeah.
Do you think it's because we are like normalizing the inputs on the sphere, or?
I think it's I think this is a solid result, right? I mean, I think this is it's related to basically a fundamental level to the rotation invariant, right? I mean, the point is that So what's happening here? What's happening is that you have much bigger than d to the L and much smaller than d to the L plus 1 sample points. So you have enough sample points, enough data to fit a degree L polynomial is d to the L parameters. So you have enough data to fit degree L parameters, degree L polynomial, but not enough data to fit degree L plus 1 polynomials, right? Now you might say, okay, but there are some functions that are larger than degree L polynomial, but I might hope to fit them as well, right? But the point is that since your method is also invariant under rotation, if you fit a degree L plus 1 polynomial, you basically will be able to fit every possible degree L plus 1 polynomial, right? And you don't have enough data to, compensate for the complexity of degree L plus 1 polynomials. This is what's happening. So as long as your method has these rotation invariants, it suffers from the curse of dimensionality. So I think this is, even more generic. These results is even more generic than this. Perhaps one can prove it in a completely abstract form, right? Just using.
So what should we think of changing, say, the activation function or the depth as doing here? This theorem is independent of these things. So, like,
yeah, it's independent of the activity. Of course, this theorem will not hold. It might not hold if the kernel becomes extremely singular, right? When the number of layers goes to infinity, for instance. So here I'm assuming somehow that these coefficients stay bounded away from 0. Again, that assumption is not necessary, really. You need only the coefficients up to degree L to stay bounded away from 0 of the Taylor expansion of the kernel. But if you let the number of layers go to infinity, then it can happen that some of these coefficients goes to 0 or go to infinity, etc. So formally, this theorem might fail there. If the number of layers becomes much larger than the dimension, or diverges with the dimension, right? Yeah.
It will also affect the
but I would be very, very surprised, really. Yeah.
It also affects the little o of one prefactor, right?
Right.
And then are n and d going to infinity here?
Yeah. So here I'm assuming, here it's implicit to the fact that d is going to infinity and n is going to infinity subject to these constraints.
And so for other kernels that are not rotational invariant, do you expect something very different to happen? Or?
Right. So for instance, okay, good question. For convolutional kernel, okay, remark okay, stop numbering the remarks. For convolutional kernels, of the structure that I described, of the form that I described before, if F star is translation invariant, of course, convolutional kernels, as I described before, only capture translation invariant functions. Okay? What is an example of a translation invariant function is sum over I 1 to d xi plus 1. This is a translation invariant polynomial on the circle. Okay? If this happens, so you get a same result. If x is always on the sphere, we get same result with the power of d less. Namely, if you want to fit a degree L polynomial, you need only d to the L minus 1 sample points, sample data. And this makes sense because basically the number of polynomials of degree L that are translation invariants is not d to the L, it's d to the L minus 1. And in fact, there is a general abstract theorem for other groups. But okay.
And maybe another question, the fact that the x is on the sphere, how important is that? Or it's just not important?
Well, you know, so that again is important, and okay, so perhaps yeah, okay.
Like if data would be generated by mixture of two Gaussian, that would be completely.
Right. So, okay. So let me give you another open problem. Open. So there is a generalization of this theorem for other, let's say, high-dimensional isotropic distribution. So similar theorem. Okay, perhaps I should write. Okay, remark extension. A similar theorem for other high-dimensional distribution. For instance, these cover cases like uniform on plus minus 1 to the d. Okay, uniform of the hypercube. This is one case. Or I would expect that it holds if you take uniform, you know, a product measure under some nice condition and things like that. But we have a general abstract theorem for nice high-dimensional distribution, and open problem. What happens for distributions with a latent low-dimensional structure? We know that, for instance, images don't lie uniformly on the sphere. That is white noise, but you know, perhaps they lie on some manifold or some low-dimensional subspace or some more complex structure. So what happens to this theorem? We have, or to similar theorems. There is one very specific example that we studied, and the example is one case is the following. You take x to be u x1 plus u orthogonal x2, right? Where u orthogonal is a d by d orthogonal matrix. Okay, so this is d by k, and this is d by d minus k. Okay, so in other words, let me draw a picture. The picture is that, okay, I'll do the picture in 2 dimensions. So this is RD, and then this all is RD, and then you decompose this in the span of U and the span of U orthogonal. And then we assume that the x1 is, so perhaps let me put here a coefficient alpha. x1 is uniform on the sphere, and x2 is uniform in the other sphere. Okay, perhaps I'll write it like this. Rho 1 as d minus k rho 2. So there are 2 radii, rho 1 and rho 2, and x1 is uniform on the sphere in k dimension with the radius rho 1, and x2 is uniform on the sphere with the radius rho 2. So this means that the data points basically are aligned. If rho 1 is bigger than rho 2, they are basically on an ellipsoid. Okay? And so we take this k much smaller than d, and then things happen. But okay, this is of course a as low-dimensional structures go, this is really the simplest example that we could think of. We couldn't make it simpler than that. And still, that took some work. Okay, but it's an interesting question to look at other cases, right? Because, so here, conceptually, what we had in mind is that, okay, this is, if you think of an image, for instance, if you look at it in Fourier domain, the low frequency components have larger variance typically than high frequency components, okay? So this corresponds to low frequency and this corresponds to high frequency. Okay. So perhaps I erase here.
Sorry, did you say you studied this case? And if so, what happens?
What happens? Interesting. So this is taking me into a this lecture is going to take longer than I expected. So we study a case in which D, this is some D to the alpha, okay, and then let's say that rho 2 is equal to 1, or let's say that rho 1 over rho 2 is some D to the beta. So why this choice of polynomial scaling is why? Because if you take a constant of the dimension, basically not a lot changes, right? But if you take a polynomial of the dimension and this ratio of the radii, I should say this is always with Theo, that is, again, the world expert on this, and with Song, and with Berus-Gorbani. So if you take this, then basically the same picture that I gave before holds, but now what matters is not D to the L, but some effective dimension. There is an effective dimension that is a combination that I don't remember of these two, and what matters is the effective dimension to the L. You understand this, right? If rho 2 was equal to 0, right? So if these were completely aligned with this subspace, the CN theorem should hold, except that D has to be replaced by D to the alpha, right? Because, okay, they lie on a sphere, except that the sphere is lower dimensional, right? Okay, so now let me say a few things about the interpretation of this. So interpretation of this result. Well, this clearly says that I'm fitting perfectly the, you can always decompose this error. This error is what? Is the L2 norm of f hat minus f star. L2 square. This is what this is by definition. So you can always decompose it in the contribution of the error due to polynomial degree L plus the contribution that is due to polynomial of bigger than L. Okay. And this theorem is saying basically that this part is 0, and this part is equal to whatever you would obtain if this f hat was 0. Okay? So I'm fitting perfectly. In a sense, f hat is the projection of f star onto polynomial of degree less than L. So you're fitting perfectly. You're fitting well everything that is of degree less than L and nothing above that. So this is first remark, first fact. Second fact is that, well, interpolation is optimal. This is you should, putting lambda equal to 0 is optimal. So this is the second example after, is optimal, in the sense that, up to these small o terms. So you might improve this small o, but so this is the second example of this benign overfitting the phenomenon that I'm giving to you. And in particular, if P bigger than L of F star goes to 0, so if this is basically, if F star is well approximated by degree L polynomial, then the excess risk goes to 0. Okay? And so if you want to draw a picture, so I'll draw a picture of the risk versus log n over log d of the, and this will behave like this. So will be basically flat between integers. Okay. And this level, this is the projection onto and this is the projection onto degree bigger than 1. And this is the projection onto degree bigger than 2 of F star, and so on. And in between it has some plateau. This is the picture that we get from this theorem. And okay, if we want to be a little bit more precise about this, we can think of F to be the decomposition decomposed in two parts, one that is smooth and one that is spiky. This is the terminology that people already introduced. I don't remember in which paper. But in this case, the smooth and spiky decomposition looks like this. The smooth part is just the projection onto degree less than F, L then of F star. And the spiky part has the property, has two properties. The spike part at the point xi is large, so is F star of xi minus the projection F star of xi. But the spiky part is small L2 norm. Okay, so the picture that we have is that we have these data points. And the way this kernel ridge regression fits these data points is that it fits a smooth part and this is why it can get to benign overfitting, why it can get rid of the noise, plus a spiky part that is very small spikes, is small in L2 norm. So this is something that can happen in high dimension, that you have something that is large at a lot of points, but is small in L2 norm. This is difficult to do in low dimension. Okay, so the blue part if F smooth. So here we have another, I think, interesting open problem is understand open. So I drew this picture, but I don't really know what is the geometry of this spike. I would be very interested to understand, are these spikes some low-dimensional structure, or they are, just some bumps, or, okay, structure of the spikes. This is interesting because the structure of the spikes tell me what happens if you test the test function at a perturbation of a train point, at a test point that is close to a train point.
I have a question.
Yeah.
Do we know how would it compare if we simply did a polynomial regression?
Yeah, would be the same.
It would be the same.
Right. So one other way to say is that the risk is the same as the risk of polynomial regression with respect to polynomial of degree L.
So polynomial regression would still have this benign overfitting.
No, because it wouldn't interpolate. Polynomial regression would give you the spiky, the smooth part. Right? The smooth part is a polynomial of degree L.
Okay, got it. Yeah.
Okay.
I see. So the risk would be asymptotically the same.
Okay, now drawing this picture, I drew this picture. There is a natural question that you might want to ask, especially if you're a physicist, I would say.
What's in between?
Yeah. Yeah. Are you a physicist? Sorry?
Yes.
Yes. Right. Now, physics like the border cases, critical regions, and everything happens there, right? So what happens here? Okay. So this is in fact something that was studied recently. So there are, it's just show that this is an interesting area or a hot area. I don't know if it's interesting, but for sure it's hot. I wish I could say the opposite. But this was solved for this case on the sphere and for hypercube in 3 papers that came up within, 1 week from each other?
Yeah, a month.
A month from each other. So the first one was by Theo. No, yeah, the first one, and then was one by Yulu and a student, perhaps is here, no? And at Harvard, and one was by Jeff Pennington and a collaborator at Google. Okay, so this is, let me see here, it's, so this thing +2. Okay, so you can find it solved in 3 papers, so you can read 3 papers about those things. Okay. And what happens, Theo?
Oh, you can have spikes depending on the Hamid coefficients of the of the kernel. Like at each, like when you cross each integer, you can have a spike.
But basically what happens is that, okay, what happens in between that, all that matters, you fit perfectly whatever is polynomials of degree. If you are here, you fit everything that is perfectly, everything that is polynomial of degree 1. Everything that is polynomial of degree 3 of larger, you look at it, it looks to you as noise, basically. It's, you have too few, you are taking, basically what's happening here is that you have a polynomial of degree 3 and you are sampling it at n² sample points. You can do this. You can take, an example of this is you take the unity interval and you take a cosine with a high frequency, a frequency 100, and you sample it at, or frequency 1 million, and you sample it at 100 points. It looks to you like white noise. The same is happening here. You take a polynomial of degree 3 on the sphere, and you sample at n² points. It looks to you like noise. So everything that matters is the component of degree 2 of the kernel and the component of degree 2 of the target function. And the component of degree 2 of the kernel, now what matters is the design matrix. So this is a degree 2 polynomial, random matrix. And this basically behaves like a Wishart. This will be with constant aspect ratio. And if I remember correctly, this behaves roughly as a Wishart matrix. Okay, so all of these transitions basically are controlled by the same formula. And what matters are just the coefficients that might change, right? The coefficients of the degree 2 part of the kernel and the degree 2 part of the function. So there is a universal formula that gives all the shape of these spikes. And these spikes can be all different. So you can have 2 to the n double descents.
Is it a kind of spikes that go away with regularization?
Is it the yes?
So if you leave the world of rotationally invariant kernels, you don't expect to have such high degeneracy for your eigenspaces. Generally, they'll be simple or very low degree. And so like, do we expect this proliferation of spikes when you cross each one? No, we just expect it to be pretty nice.
Yeah, we expect this thing to be, basically. I would expect now. Is there any result of that type? I don't think so. But I would expect. I mean, in this generalization that I stated, we assume a gap, right? And I would expect that this decreases, but there is not this plateau necessarily. So this plateau, you're right, depend on the.
So if we have say an even kernel function, we cannot learn an odd function, right? So
yeah.
Is there some other condition on the?
Yeah. So this is the condition that I raised, but I brought some point that is, all the CL are strictly positive, right? If they are not strictly, if there are some of these coefficients CL are 0, well, that component of the function you will never learn. Okay. Okay. Now I'm through 1/3 of this lecture that I planned, but it's good. It's very good. So I want to give now an intuition of why all of this happens and some of the math of it. I think the math is quite interesting. It's quite interesting because you start from something, you end up studying random matrix models that are a bit different from what people have mostly studied. For instance, random matrices with very large aspect ratio, and or with these polynomial dependencies between the entries. So okay, you can. Okay, so what I want to describe is a little bit the structure of the kernel. Empirical kernel. That it's Kn. This is so first of all, let's look at the population kernel K. Since it's an inner product kernel, K diagonalizes. So we saw already that K can always be diagonalized, but in this case it diagonalizes in the basis of spherical harmonics. Okay, so I have to give you tell you a little bit about spherical harmonics. So what are spherical harmonics? For any L in integer, this includes 0, you have d to the L spherical harmonics. So these are functions on the sphere, x, so x in the sphere of radius square root of d in d dimension. And so you have, let's say, d to the L, d of L, dl of them. So L1 of x, y, L, dl of x. All right, so these are dl functions. And these are what functions? One way to define these are what? So these are degree harmonic polynomials, homogeneous harmonic polynomials restricted to the sphere. Right? So you take an harmonic polynomial, a homogeneous harmonical polynomial in Rd, and you restrict it to the surface of the sphere. And you can you can arrange things in such a way that these are orthonormal. So L I Y L prime I prime or L K K prime. This is delta L L prime delta K K prime. Okay, so they form an orthonormal basis of the space of square integrable function on the sphere. And the degeneracy, what is the degeneracy of this space of the degree L? Well, how many polynomials there are of degree L, linearly independent, roughly d to the L. Well, since there is permutation, roughly d to the L over L factorial. Let's say d to the L to make things simple. So it's a little bit d to the L because of permutations and degeneracy, but let's call it d to the L. Right, so these are, and obviously, obviously, what happens, you can convince yourself, is that if you rotate x, the subspace of function, the span of this function transforms into itself. So the space of this function is invariant of degree L polynomial, is invariant. If you rotate a degree L polynomial, it remains a degree L polynomial. So this space is invariant, and this is why an invariant object, an invariant kernel diagonalizes in this basis. And okay, what is this? This is, of course, the product in L2 of the sphere. Okay? So this means that I can construct a projector PL. So the projector onto degree L polynomial, you can view it as a kernel. The projector onto the span of these functions, you can view it as a kernel. You can implement it as an integral operator with a kernel, and this will be, of course, will be the sum over J1 to d to the L, dl of y L j x1, y L j x2. Okay? This is, if you have a subspace, how do you construct a projector onto that subspace? Well, the projector onto that subspace is, the projector on a subspace V in general, and the finite dimensional space is the sum over one dimension of V, Vi transpose, right? Where Vi is an orthogonal basis of the subspace V. And this is what the same that I'm doing here. X1 and X2 are the indices. So if I look at this, M, N, or X1, X2, X1, X2. Okay? So, are you okay with this formula? No?
Define it this way?
No, this is, I claim that, okay, if you have a set of orthonormal function, Wi of x, and these are orthonormal, the function that they are orthonormal, okay, in L2, how do I construct the projector onto the span of this function. The projection, so V, the span of the phi. How do you construct the projection of V? Now, the projector on V has a kernel, so can be written as an integral operator with a kernel, and the kernel will be the sum over I1 to D phi x1 phi x2. This is what I'm saying. So I can write this, of course, as YL transpose x1 YL x2. And now my invariant kernel, my inner product kernel, kx1, x2, of course, diagonalize, and all the eigenvalues along these subspaces must be equal by rotation invariant, so I can write it as infinity of some coefficient lambda L square. This must be non-negative because the kernel is PSD times YL x1 transpose YL x2. Okay. So this is the structure of the kernel. You can write it with spherical harmonics. And okay, let's take that lambda 1 square bigger or equal, or lambda 0 square. Oh, they don't need necessarily to be bigger or equal, but okay. So now, so what is the typical size of these eigenvalues? This is useful to have in mind. Well, the trace of this kernel, this is the integral of, we said, kxx mu 0 mu dx, where this is the uniform measure of the sphere. And well, you know, let's say that this will be finite if sigma prime, for instance, finite. And so what you get is that the sum over L 0 to infinity lambda L square is finite. Lambda L times, okay, the dimension, the trace of this is d to the dl. So this is finite. So it means that lambda L square is less than d to L to the minus 1. Okay. So the Lth eigenvalue of this kernel must be of order d to the minus L. In fact, you know. Okay, in fact, I will not go over this calculation because it'll take me 15 minutes. So I'll leave you as an exercise. It's actually a nice exercise. In fact, under our assumption, lambda L square is basically CL over d to the L, where CL are the coefficient of the limiting. Remember, there was this h of q that was sum over L 0 to infinity, CL over L factorial q to the L. And this is related to this thing. So the expansion, you know, the kernel was an inner product kernel, the function that, you know, this was h of hd of x1, x2 over d, this function here. I said that this you can Taylor expansion. This was my exercise number 1. Now exercise number 2, I'm giving open problems and exercises, so keeping you really busy. So the coefficient of this expansion, I assume them to be non-negatives, and I claim that these are related to this modulo. So this is not only an upper bound, but it's actually the right order of these eigenvalues. Okay? So this is the structure of the population kernel, if you want. The structure of the kernel as an operator is a sum of coefficient times this spherical harmonics terms. So now I know all the eigenfunctions and eigenvectors. By the way, this is one reason why we like working with this problem on the sphere, because we know how to do harmonic analysis over the sphere in any number of dimensions. This is harmonic analysis. This is why we like to do it, or Theodore likes particularly the hypercube, because harmonic analysis over the hypercube is even easier than harmonic analysis over the sphere. Now, if you go to product measures, it becomes a little slightly painful. I would say slightly painful or slightly more exciting, depending on. If you look to convolutional kernels, also becomes painful for other reasons.
What are the eigenfunctions for translation invariants?
What are the eigenfunctions for translation invariant things? I don't remember. Do you remember?
It's I mean, it's translation invariant.
It's translation. Yeah. So you take, So you take the spherical harmonics of degree L. I wrote them to you, right? I mean, I didn't write them, but these are polynomials. There is a subspace, a linear subspace of this space that are the translation invariant spherical harmonics, right? You can just construct them very easily. You take any spherical harmonics and you average it over translation. When you do this, you lose dimensions, of course. Degree L polynomial you lose will be, instead of d to the L, you will lose roughly factor d. Right? And then that will be the basis. And yeah. Okay, excellent. So the empirical kernel. So this was the population kernel. What is the empirical kernel? Okay, so this is again what it is Kn, which is K. Okay, so just I can decompose it using the same formula, right? So you obtain it by evaluating this formula of at the point xi, xj. So what happens if you do that? You obtain the sum, so I'll write it as the sum of two terms. And then so this at the moment is not particularly useful, but it becomes in a second useful. Where ym is what? Y at m is simply obtained by evaluating these polynomials onto the n data points. Okay, so for polynomials of degree m, you have a basis vector, a vector of polynomials. So there is dm of them, and I evaluate this at the n sample points, right? And so this gives a matrix that is n by dm. Okay? And then I take the matrix times is transpose and the matrix times in transpose. So this is just obtained by substituting points xi, xj in that formula. So this is k n less or equal than L, the low degree part of the kernel, and this is the high degree part of the kernel. And now the low degree, what happens, the crucial thing is that these two parts have a completely different behavior. And you can see that they have a completely different behavior because if m is less than or equal than L, then this is a very skinny matrix. So Ym is skinny. because n is, we said, bigger than D2DL, much bigger than D2DL. So this is an extremely skinny matrix. So this matrix is a low rank matrix. It's low rank. It's very low rank. And if M is bigger or equal than L plus 1, then this is a fat matrix. And so this is full rank. So this starts to saying that these two parts of the kernel behave very differently. And this is really the crucial business in this case. Of course, you see also that from this that if n is proportional to d to the L, then there is one term here that is the term, the Lth term, in which this matrix has constant aspect ratio. It's neither skinny nor fat. And that will behave differently from the other, and that really drives the transition thing. So this is what I was saying before, this matrix. Okay, perhaps 1 second. So now these matrices behave very differently. Let me say how they behave in a moment. So let's look at the skinny case. Let's look at M less than equal than L. Then if I look at Y M transpose Y hat M, divide by 1 over n. This is what? This is 1 over n, sum over I 1 to n, y ym xi transpose, ym xi, ym xi transpose. These are vectors, right? And this is d L by dl matrix. Each of these is d to the L vector, right? And now you have an average and a large number of matrices, and n is much larger than d to the L. You can prove that this is close, or you can hope that this is close to the expectation with respect to x of ym x ym x transpose.
So isn't the dm?
Dm, sorry, thank you. Okay? And this can be, okay. In my original plan for this lecture, I was proving this, but now I have 1 minute, so I will not prove this, but this is proved by matrix concentration, matrix Bernstein. Okay? So you had some random matrix theory, I think, but I don't think you saw this. I think this is the single most useful result in random matrix theory that you can learn. And what is this? This is the matrix of inner product of the spherical harmonics, right? So this is the identity matrix in the dimension. So what does this mean? It means that y hat is basically up to the scaling square root of n, basically an orthogonal matrix. So this means that the kernel less or equal than L is basically sum over, let me now put together, is approximately the sum over M0 to L of CL. We said that lambda square is CL over L factorial. And then there is a factor n that comes from here. And then is really CL over L factorial times d to the L. And then there is the factor n. Okay, and then, m. And then um transpose, right? Where these are orthogonal matrices. So this means that the first eigenvalues of this matrix I mean, this matrix has eigenvalues at scale n over n, n over d, n over d square, etc. And there's one eigenvalue of order n, roughly d eigenvalue of order n over d square eigenvalue of order n over, so there is one eigenvalue of order, let's do it like this, 1 of order n, d of order n over d square of order n over d square, and so on. Okay? And a certain point, when you arrive at d to the L, there will be d to the L eigenvalue of order n to the dl, and below that there is nothing in this part of the matrix. Okay, so I'm done with time, but okay, a claim, okay, one proves then that the high degree part is approximately a constant, let me call it, I don't know, kappa, times the identity matrix in operator norm. Okay? So this means that all the other eigenvalues are of order 1. So n eigenvalues of order 1, roughly n eigenvalue of order 1. So this is the pattern of eigenvalues. There is one very large, d a bit much smaller, until you hit 0. Right? Now, doing kernel ridge regression, this means that doing kernel ridge regression, this is basically equivalent to the kernel of the projection of the original kernel onto polynomials. So this is doing polynomial ridge regression. And what is this thing doing is adding a ridge regularization to an effective ridge regularization to your kernel. Okay, so what happens is that, exactly as we saw in the case of simple linear regression, lambda goes to lambda. So you get that ridge regression, kernel ridge regression with the original kernel becomes polynomial ridge regression. Kernel ridge regression with lambda becomes polynomial ridge regression of degree L polynomial with the regularization lambda plus this kappa. Okay, so you have an increase in the effective regularization, exactly as we saw for simple features.
Here CM is real formula for CM.
CM is the Taylor expansion on the so HQ, if you remember, this is sum over L equals 0 to infinity, CL over L factorial, Q to the L. And actually, you can compute the CL. Basically, they are related to the Hermite expansion of the activation function in the special example of two-layer neural networks there. But in general, if you give me the kernel, I can just take derivatives at 0 and compute the C's. Okay, I'm 5 minutes over time, so okay, I'll take one question.
This equivalence between kernel ridge regression and polynomial regression is only about the values of the risk, right? We don't see any benign overfitting when you take the polynomial regression with lambda plus kappa.
Right. This is my answer to Lenka. This part is equivalent in the L2 sense. So most of point, the function that you obtain here is equal to the function that you obtain here at most point. But at the test point, at the train point, the two functions will be different because this will contain the spiky components and this will not contain the spiky components.
We have a few more minutes if you want, because the next lecture will be starting at 11 exception.
Okay. We have a few more.
As a follow-up on this, but the spiky part would still be the result of this first low-range part of the kernel, or all of the...
So the spiky part will be depending on the higher rank part of the kernel, this part of the kernel.
This does not go to 0 also for into infinity.
This part doesn't go to 0, of course. This is, as I said, is approximately a coefficient times the identity. Okay, and
In the end, the claim was, not the claim, but you said like the kernel ridge
Yeah, and it's equivalent in the sense, in the L2 sense, right? In the sense that here I obtain a function fkrr. If I run this argument, here I obtain a function fprr, and the two risks are similar, so this is what we prove really, but okay, I think that if you look in the proof, what we really prove is that this is small. Okay, so this means in L2 sense, the two give the same function, the same model, meaning that at most test point, the two models are the same.
So this is the small O1 with respect to N and D.
Right. Yeah.
Been not understood, which is the role of regularization of this, where lambda enters in all the formulas. I mean, is business of the projection is independent of lambda, or?
Yeah, all of these statements, all of these statements are just about the kernel. So the kernel doesn't have lambda. Now lambda, where lambda enters in the analysis, and okay, I'm not doing the analysis here, but where lambda enters is that you remember that f hat lambda is equal to k, f hat lambda at x is equal to kx dot transpose lambda identity plus kn minus 1 times y. Right? Now lambda enters here. Now if I expand this, if I use this approximation, this is lambda plus kappa identity. This is for the high degree part. Lambda plus kappa identity plus k less or equal to nl n. Okay? So this is doing, you see, polynomial regression, because there is this term, with the shifted lambda, right? And yeah, so now if lambda is small in this intermediate region, the point is that this guy now has all eigenvalues that are much bigger than order 1. The smaller eigenvalue of this, lambda mean of this, is bigger than n over d to the L, is much bigger than 1.
So,
right?
So the lambda does not kill any eigenvalue.
Yeah, so this doesn't matter. Now, if you go to the region, so this is why regularization, you have this flat region, in the risk as a function of log n over log d. There is this flat region, and here the regularization doesn't matter. Now, as Theo mentioned, when you go in these intermediate regions, then what happens in this, that this fellow hit order 1 become of order 1 because n is proportional to d to the L, and therefore the regularization starts to matter. So this intermediate region, it matters whether you regularize or not.
So the fact that here you have a huge degeneration is useful to make lambda not matter, because
right.
Okay.
In a sense. Okay, thanks a lot, and sorry for going over time.